Hello, everyone. Welcome to the second webinar, which I'm holding. The last one was on parsing. So if you missed it, I suggest that you go and watch. And today we are going to talk about C++ semantics, which is kind of a topic related to parser, but also it's kind of its own topic. Okay, so my name is Yuri. I'm an architect at PVS-Studio. I'm working on the static analyzer on the C++ part. And let's go. Let's talk about C++ semantics. I won't touch the depth of code. I would like to show you code from a semantic analyzer, but it will take a lot of space and a lot of time because there's a lot of it. So I'll talk about semantics in principle. Okay, let's begin. As we are working with a language, a programming language, we have all the features that other languages have, namely syntax and semantics. And if we look at definitions, syntax is a way to form a valid sentence in a language. This is what a parser is dealing with. It takes the language grammar and makes sure that what is written is valid syntactically. And semantics is the branch of linguistics and logic concerned with meaning. And why linguistics? Because I think programming languages and natural languages are kind of related. So last time we looked at the famous Fox example. And in terms of parsing, we made it into a binary expression. And kind of the verb was an operator and the two operands were fox and dog. But semantically, if we look at it, we can assign meaning to those things. So right now, jump isn't just an operator, fox and dog just some identifiers like variables. But if we look at, so to speak, implementation of those things, we can kind of put what they do and what they mean. So like jump is an upward acceleration, over means essentially above, fox is an animal, it's a of the kind fox, and so on and so forth. So we can assign those meanings to all the entities participating in a sentence or in an expression or whatever. Let's look at an example. Okay, so we have two structures. We have an operator, which kind of describes addition of objects of those structures. And let's say we have a function like that, which returns a sum of them. The same thing as in the example with fox and dog. It's a binary expression. And the meaningful parts of that binary expressions are the operator and the two operands. And of course, the operator is a function, as we have defined it. And variables are two variables of different types, which can be added together. This is still syntax, because syntactically, this code can be parsed quite easily. But semantically, it might make no sense whatsoever, even if syntactically it's correct. Okay. If we delete the operator and we no longer have it, this line here in return is going to fail. It's not going to compile because we do not know how to concatenate, how to add together variables of these types. And if you are observant, you can see that since we have not defined our structures, this also fails because we cannot create objects of incomplete types. But syntactically, this is fine. This is okay. And by the way, I completely forgot to tell you about the format of this webinar. I was carried away, kind of. If you have any questions, please write them in the chat. You may write them down in the chat as I speak. When we finish this, I will be able to answer the question you might have. Okay, sorry for that. Moving on. How do we know which identifier means what, right? For that, we have to perform name resolution on any code we come across. Let's take a look at a simple example. I like simple examples. They are really, really obvious and kind of easy to explain. Okay, so this here code has three declarations, two functions and a variable. And when we see a call like that, we need to figure out what these words mean. So here we have a function and we also have a variable, and those words are related to each other. So here are the names we have in the program, in the entire program shown on the previous slide. And in C++, in general, in languages which have functions and stuff, things are arranged into scopes. So here we have two scopes. We have a global one where we have two functions and a scope of one of the functions where we have a variable. And these names, they are represented as symbols, so-called symbols in our program. Well, a symbol is just some kind of meta information about a name. To figure out what a word means, we need to have a symbol table, a way to make names mean something in terms of some kind of information represented in code. Let's take a look at how a symbol table might look like in your parser, semantic analyzer, static analyzer, whatever, in your whatever program which works with source code in a language. Well, there are two approaches to that problem. How to create that thing which allows us to resolve names. So one approach is scope-based, and the other is name-based. They're kind of similar, but kind of different. So in a scope-based approach, what do we have? Let's say we are inside a function, it's a scope, and all the names declared in that scope go into a hash table. And the scope has a parent scope because we have a scope hierarchy, and it also has a hash table of names, and so on and so forth up to the global scope. And with this approach, you might see a problem here. If we start from some scope and try to find a name in it, what we'll have to do is check, okay, does this scope has this name, which means a hash table lookup? Let's say it doesn't have a name. So we have to jump up and perform a lookup again and again and again and again, up to the very top. And the problem with that is if a name does not exist in a program at all, and we have to look up names a lot because every declaration of anything might be a redeclaration of something which already exists. So when we parse a declaration in C++, we have to check if it's the first one or if it's a repeated one. So if a name does not exist, you will end up traversing the scope tree all the way up to the root and perform a name lookup at every step. This approach can be used, but I think it's inconvenient and it performs a lot of kind of extra unneeded work. So a name-based approach, what is it? We have one single hash table of names. Name is the key inside the entire program, and all names go there. And every name we add has a scope list associated with it. So let's see, we have name 0, however many names we might have there, and every name has a list of scopes in which this name is declared in our program. Let's see an example. In the previous piece of code with 2 functions and a variable, we had these names. So now they are going to be our keys into our hash table. And we also have an extra name, a fake one, which I'm designating with this brave accent. This is a name of the global scope. You don't have to have it because we'll never look up a name for any artificial entity like that. But in order to associate a symbol with it, we will have it here. Okay, now we have names. We need to assign scope lists to them. The global one is not located in any scope at all because it's already global. So it doesn't have any parent scope. Our functions, both, are declared in the global scope. So this one is going to be their parent, and the variable a is a parameter of a function. And so it's declared in the scope of that function inside it. And those scope lists, actually, they're also kind of hash tables where a pointer to the scope is the primary key. And they have symbols attached to them. For the global one, it's a scope. Here we have 2 function sets. I will explain it a bit later. And a is a variable. All right. And let's start from the simplest one, simplest kind of name resolution in principle, but not so simple in practice. Unqualified lookup. Well, you know, while working on parsing and semantics, I figured out when that then something is labeled simple, it's not so simple, but let's see how it goes. Okay. Again, this is our code, which we had previously. And we will be inside the function body, and we will be looking at a function call. And we want to figure out what this name means. So how do we do that? Well, it's simple, really. We just go and look it up in our huge table of names, which we find because it's there, it has been declared. And right now, we are located here in the scope of the function itself, because the call is inside the function body. And as you can see, the function we are calling is not declared anywhere within that scope. So since we do not find this scope meow inside parents of per, we will just jump up. The function scope has a parent, which is global scope. So we'll just jump here and check it here and see if we can find the global scope in the list of scopes associated with the name we're looking at. Okay, and yeah, since our function is there, we can easily find it. And we can conclude that this word means a function set which contains of one element right now declared in the global scope. And the same thing is true for the variable, for the function parameter, which we have inside there. So unqualified lookups work in a way that they find a name and jump the scope tree upwards from the current one to the parent and see on every step if the name is declared in that scope, and they return when a name is found. Okay, so that's not the only situation, and that's not the only way we can write our code, because C++ has namespaces, which is a good thing, and simultaneously can be a trouble if you are parsing and looking up things. But in this case, okay, let's assume that our function is in a namespace and we call it like that with a qualified name, with a name resolution. And here we have a qualified lookup. In some sense, the qualified lookup is kind of easier to do than the unqualified one. But first, let's see how our symbol table changes here. So we have an additional name in the global scope, and the function we are calling moves to that namespace associated with that new name. And if we start looking up from the beginning, of course, from the first part of the compound qualified name, we will perform first a usual unqualified lookup as we did previously, because the thing here is the unqualified name, because the qualified name starts with it. Okay, so we can find it and we can remember that we have found it because we'll need it for later. For the next part of the qualified name, we will find it as usual in our symbol table, but we won't perform those jumps upwards and so on and so forth, because we have previously found the parent scope, which was explicitly stated in the code. We can go directly into that namespace instead of jumping and trying to figure out where our function is located. And here we check only for that specific namespace. If the function is not in the namespace, it's a failure. It's an error. In this case, of course, we are lucky because I wrote the code so it can be found. And yeah, we can find it like that. Quite easy. So when we were looking up the qualified name, here are the two entities we found. Okay, qualified and qualified lookups are kind of straightforward, but there is one additional lookup which is kind of obscure, and I'm not sure whether or not people even think about it. I mean, everybody uses it all the time. Well, not uses it. Everybody writes code which ends up in this lookup on the compiler side all the time, but I think many people do not even think how it works. Okay. Probably you may have guessed by now what I mean, but let's see this. Let's see this example. So we have a namespace and a structure in it and a function which accepts an object of this structure as its parameter. And somewhere we have a call like that. Like we declare a variable and put it into the function call. And this compiles. It compiles just fine. It's a valid C++. It's not a problem, and so on. Even though it would seem that the unqualified lookup shouldn't be able to find that name because it goes up the scope tree, and our function is in the global scope and our namespace is also in the global scope. So we just go up, we get to the global scope, and the function is nowhere to be found on that way up. But still it compiles. Okay, so here we need to make a little detour and talk about the concepts of visibility and reachability in C++. What are they? So let's say you have a function, and inside that function, you declare a structure. That structure, this one right here, you cannot address it by name anywhere outside the function. And this one is not visible by any means outside. But we can still use it. We can still reach it, and we can still access its members. We can still figure out its type, and so on. Since our function returns this structure, this code is also valid. We can infer the function return value from the internal structure, and everything will be accessible to us if we just return it. So the structure is reachable outside the function where it's declared. This visibility, reachability stuff is related to modules a lot, because in modules, a new feature in C++, you can restrict what is imported and what is not imported, but it can still return objects declared in private parts of the module, but you can't address them. Okay, so the other situation with visible and reachable dichotomy here is if we have public and private members of some structure or a class. Let's say we have a function, and let's call a public function, public member of our structure. This one is both visible and reachable outside of the structure itself. The name is, by the way, resolved by using the qualified lookup when we use the dot member access. And this one is a private function of structure, and surprisingly, it's still visible, but not reachable. If you look at your compiler, when you write code and try to call a private member, it will be found. So access modifiers, they do not affect visibility. They do not filter names out of lookups. They just do not allow you to use them because that's where the semantics analyzer takes into account that those members are private or public or whatever. Okay, so let's see how it goes when we try to understand what function is called here. It's an unqualified name, so we use an unqualified lookup. And again, we find the name, we search the function body, and all the way up to the global scope, it's not found. But in this case, we know that something passed to the function as an argument. We know its type and we know where it's declared. And when we do an unqualified lookup on a function, what we also do, we take all the arguments passed into that function and include their namespaces also in the scopes we are going to search. So here we just go to the namespace, and there this function is found. And it happens all the time, and this is called argument-dependent lookup, or ADL. I said that people use it all the time, well, because everybody is kind of familiar with overloaded operators. And overloaded operators, like for example, you want to create an operator which prints something in the outstream. Those operators are typically found using ADL because you typically define them and declare them and define them next to your custom classes in your custom namespaces, and they still work. Anyway, so using ADL, we find usually functions which are not visible from the point of the program we are located at, but they are still reachable. Because in principle, you can access a function from different namespaces. Speaking of namespaces, C++ gives us an ability to kind of steal symbols from their scopes. Because we can do using something, and after that, we can just address it by an unqualified name. So here in this example, we are importing one name from a namespace. And in our symbol table, this is quite a simple thing which happens. We just add this name to our current scope. So the way it works is as if our function would declare the other function inside of it. So we end up with a picture like that. The name from the namespace is kind of declared both in the namespace and inside the scope, which said using new. Of course, here we do not copy anything. Symbols are stored in their own location, in their own storage, and here we are operating typically with pointers to symbols. So our symbol table now for name has two scopes which have pointers to the same function set. And to kind of explore this further, let's look at this example here. Let's say we have a variable in a namespace. We are using this variable inside a function. We also have like kind of conflicting names in the global scope and along the way. But here in return, we find the one from the namespace because we do not go all the way up. We look inside our function scope. We do not find a variable there. And then we kind of find it in the namespace scope. If there was a local variable with the same name, it would have been found first because it has priority. And another situation is when we are using namespace or using enum. I think there are two things, namespace and enum, which you can use in like that. In this case, the search is a bit more complicated than was before. Let's see how it goes. Again, we are looking at a function and we want to find it, and we can find its name. So far so good. But to explain how this search performs, we have to switch the perspective a little bit. And let's see, let's look at the scope tree of our program. Now, we are here. Our function imports the entire namespace into it. In this case, of course, we cannot just take all these symbols from the namespace and add them to the function scope. It would be dumb. So what we do instead, we perform an unqualified lookup, the regular one, where we jump the scope tree, but we keep track of all the imports which we come across along the way. In this case, we start looking for our function here in our other function, and it's not there, no surprise. And there's no direct path from the imported scope to our current scope. So we cannot climb from thing, we cannot climb directly to meow. All right, at this point, we do not even consider symbols from thing. We just move on with our unqualified lookup. Okay, next step, we climb here. And again, our function we are looking for is not in the global scope, but from our imported scope, there is a direct path to this point. So here we will go and check, is the function in that imported scope or not? And what do you know? Of course, we find it because it's there. So you might ask, like, why? Why do this? Why so complicated? Why consider some direct paths and common parents of different scopes to just perform a search? Why can't we just, from the place where we say using namespace, why don't we go from there and look for symbols from that namespace? Oh, let's look at the example again. In this case, no surprise, we find the variable from the namespace. It's expected. But in this situation, we have a local one, and we find it using the unqualified lookup. Again, no surprise here. Let's go a bit deeper. We still find that. And that's logical because we climb scopes, right? But it's kind of logical, but kind of not, because using namespace is written in a nested scope, and according to logic of how it's written, we would have to find the variable from the namespace, but still we find one which is higher but closer, kind of, the local one. But this is suddenly ambiguous. If we have a global variable, this is going to be an error. And this behavior is according to the standard. And we start actually checking, searching where the our name is in the imported scope. We start searching for it here, not deeper inside. Even though, as you can see, our using namespace is written all the way down inside the function, inside the nested scope, inside this function. This is a difference of importing a symbol directly and importing an entire namespace. When we import things directly, with this example, with the global variable, we would have still found the one from the namespace. And by the way, in this example written down below with a nested scope inside a function, if we said using thing variable, we would have found the variable from the namespace there and not the local one. Okay, I think enough of name resolution, but kind of not enough of name resolution yet. Let's look at classes. Classes are quite an interesting thing in C++, because in your quote-unquote normal code, you can only find things which have been declared previously somewhere. But classes work differently. And this is, by the way, where semantics starts affecting parsing. Let's look at this structure. Okay, we have a function which calls another function. We have another function which assigns a value to a field, and we have this field. And if you just go and parse your class, and we also go like top to bottom, left to right, you will come across the body of this function before you come across the declaration of the field here. Let's ignore the first function by now. And this won't compile. This wouldn't compile if you just did parsing like that, top down. So classes, we cannot parse them in a single pass. We have to kind of traverse them twice. So what we do here in the parser, when we are inside a class and we want to deal with class member functions defined in line inside the class body, we have to skip them. So those bodies, they're not immediately parsed. We kind of postpone them for later. And as a result of the first pass, we essentially have that. So we will just have a class and all the declarations of all the things declared inside of it. Because here, the class type is incomplete and you cannot access anything from it. You cannot create objects of this class. You cannot call its functions. You cannot access its data. You can only see declarations of stuff. And it becomes complete only when you exit the body of that class. And here is where we actually parse function bodies which are located in our class. So we kind of do something like that when we see a class definition, but not exactly. Of course, we do not create like additional declarations outside of class. We just parse them into different passes. And now we can find everything in those functions, no problem, because we already have all those things defined. Let's talk about function overloads. Classes, name resolutions are fine, but how do we know which function of the multitude of overloads to call? All right, let's say we have like 4 functions like that somewhere in the global scope, and we want to call something, some of those functions by giving it some arguments, just 2 ints. Remember the function set from the very beginning? And I said that I was going to talk about it a bit later. So what is a function set? It's a single symbol. So we don't create a symbol for every function individually. It's kind of one symbol which contains a list of all functions with the same name. And when we are looking up a function name, we are operating on those sets. And if we looked up for this function in different scopes, this set would have been just expanded for overload resolution. So every function we find goes into here eventually, and this is where we have to choose which one was meant. And the call, this is important, so keep that in mind. The call accepts 2 are values of type int. It's 1 and 2. So how to figure out what was meant here? Okay, so first of all, we go through the function set, and by considering the given arguments in the call, we calculate conversions needed. So for every function we calculate, what would it take to convert this argument, considering its type and value category, our value in this case, what would it take to convert it into the parameter type? For the first one and int, it's an exact match. We do not need to perform any conversions. We already have an int. And the second argument goes to void, kind of, because we do not have a second parameter in the function. Okay, here we have an l-value reference bind on the first one and an exact match on the second. There's no implicit conversion or any way to implicitly convert an int into a pointer. Well, at least in C++. In C, this kind of works. But anyway, in C++, the first one is invalid. We cannot fit the first argument into the first parameter on that function. And the second one is the match because it's an int. And the last function, it has a match and an arithmetic conversion from int to float. Okay, so once we have collected all these, we have to then sort the list we get as a result. And like, we do not filter anything out. We do not calculate compatibility of parameters or anything like that. So we do not apply the any score system kind of. We compare all this information about conversions for each function to each other. So we can't say whether or not, like, this function costs X point and this function costs Y point and so on, but we can say that this function is better than that function by comparing those conversion information for every parameter, for every argument into every parameter. And by the way, if you watch closely, you can figure out that in the second function, this L reference bind is also an invalid conversion. Why? Because you cannot bind an R value to a non-const L value reference. If we had a const there, it would have been a valid conversion, and that function, spoiler, would be the best choice. But anyway, as we range this function list, we do not do it like argument by argument. We look at the entire sequence, but for the sake of simplicity, let's say that we look at the first conversion data first. So obviously, invalid conversions are worse than exact matches. And here, an arithmetic conversion is better than an empty kind of parameter, which we cannot use at all. So here, the best match will be this int float overload. The algorithm itself is kind of elaborate, but in essence, it just sorts the list of functions, comparing conversion sequences with each other for arguments into parameters. And when we have one function at the top, we have found the best one. If we had more than one function and they would be equal to each other and no functions would be better than them, that would be an error. And also, let's take a look at templates right now, how they work. Templates are kind of similar to functions. Let's see why and how. Let's say we have a structure, it's a primary template, unspecialized, and well, nothing special about it. We have a function, we have a field, and let's say we are really, really mean people and we want everyone to create a specialization for that template. So we put a static assert here. And if we just try to use the primary template and instantiate it, we will fail the compilation. And to encourage people to kind of use their specializations, let's say we've made one for them ourselves. But someone decides to use like a different thing. So we have a primary template, we have specializations for int, and somebody decides to put a float there and kind of accept an object in a function. Let's see what happens here. We have a template. It's a record meaning class, structure, union, these things. And we also have an explicit specialization that we provided ourselves for that template. And when we see a call like thing of float, what do we have to do? We have to substitute float for t, in this case, in the primary template. And then we have to select a specialization if we have one. And this specialization selection, it works kind of like it was a function. And so the same thing happens as with functions, only we do not calculate implicit conversions. Like float and int should match. Otherwise, the specialization is not what we need. So here float is not int. So we generate another specialization by taking the primary template as the source of kind of code. And we change things written in the primary template into our specialization to generate it. And the question is, how do we generate this new specialization which wasn't there before we said thing of float? What's going to be inside? If we do and things like that, if we accept a reference to that template, what's going to be inside the body of the structure, this specialized structure we generate for float? Well, actually nothing. Since we can accept a reference to an incomplete type, we don't have to generate a complete type at this point. We will just generate a declaration. Hey, look, there's a thing of float. Here it is. Take a reference to it. But if we remove the reference, here suddenly we have to know the class layout and size and so on and so forth. So we will have just the data members here. Anything which affects layout table. And remember the static assert we written before? Well, this still compiles because that static assert never fires. The compilation is fine. But if we dare call the function, in this case, this is where the static assert is going to fire, and our compilation will fail at this point, but not before. This tells us an interesting thing about templates. Templates are lazy. They get things declared inside them as those things become needed and not before. So let's see what we can do knowing that. Let's say we have a declaration of a template and we have another template which uses the first one. So here in the second template parameter, we are creating a default value of meow of t again, and inside we address something from that the second parameter, the type used as the second parameter. And that's okay, because m in this context is a dependent name, and meow, even if we address it by name explicitly, is also a dependent name because it's not an instantiated template. It's just a primary template which gets a substitution of some parameter. And this would be legal in this case if we declare just a function which returns our second structure of, say, int. That compiles. If we wrote a body of that function, that would fail because in this case, we would use an incomplete type. If we address something from inside of the template, of course, it would be a fail because, again, incomplete type. We do not know what this type thing of the structure of int means. But as soon as we provide the definition for the first template, it's going to be okay again. Why am I telling you this? Because there's one interesting feature which breaks this template laziness entirely. And that's what's known as explicit template instantiation. Somewhere we can write something like that. It's an awkward construct, in my opinion, to write. But if we do that, what does it tell the compiler? Well, it tells the compiler, hey, look, we have a template there. Go substitute that float into it and go generate everything in that template. Everything from the primary template should be generated, not as needed, but right here, right now. Give me all. And this, of course, fails because in this case, if we wrote something like that, we would make the compiler to generate the code for the function, which has a static assert of false, and that would fail. If you're interested, there's a blog post about these specific constructs. The slides will be shared along with the recording, so you can look at it later if you're interested, or just, I don't know, take a screenshot of the QR code. All right, so templates, well, templates are kind of awesome. They're also kind of headache. And
thank you, like newer versions of the standard, which that we can kind of restrict them and make them more specific. Let's look at how constraints work. And to demonstrate how constraints would work, let's go and make our own isPointer trait, like from the standard library. We all know and love the standard library traits. Let's make our own. What would it be like? Well, the primary template is pointer, which by default has a value of false inside it. And let's make a specialization, a partial one, which if we pass a pointer to t, it would have the value of true. And also we'll have a concept which results in reading that value from the isPointer structure. By the way, have you noticed that concepts are kind of bulls on steroids, which are really tricky bulls? They behave like Boolean values, and that's as intended. And we'll have a structure which is a template, and it wants pointer as its template parameter. Let's see what happens if we pass an int there, not a pointer. Okay, this will fail because int is not a pointer, but how do we know? So the chain of template resolution goes like that. First, we put int into t of our thing structure. And since t is restricted by a concept, we will subsequently put the int into t of that concept, which will get into the isPointer. And this is where we have to choose the specialization of our isPointer structure. Okay, so we have a primary template and one specialization, and it would seem that, well, we have int, we could have an int pointer here, right? If we just substitute for t. But it doesn't work this way, since the specialization requires a pointer. Int will not match because there's no way that we can turn a plain int into a pointer. So we have to create our own specialization for that structure. And of course, template of int generated from the primary template has the value equal to false, which results in the concept evaluating to false, which results in substitution failure, and int doesn't match. And what if we had a pointer to int? Well, let's say none of that with int before happened, and we still have a primary template and a specialization, a partial one, which wants a pointer from us. We substitute int pointer into the t of the primary template. And then, as I said, we select specializations as though they were kind of functions. And there is a specialization of our template, which has a parameter of type pointer to something. We don't know yet what, just t. If we drop that pointer, we will have a match. Int matches to t. And as a result, we will have t int and value true. And so that attempt to use our structure with a pointer would work. This entire specialization business, this is the specialization we end up choosing. This is kind of confusing at first, but to understand it better, it helps to look at templates as if they were functions. Like pretend that we have some function templated which accepts a pointer to t as its parameter, and we kind of call this function with a variable of type int pointer. And here, to fit our type of the variable into the actual parameter, we have to drop the pointers, calculate the conversion of what is under the pointer, and put the pointers back again for the actual parameters. So here, if we call it like that, like if you look at this t star, it's the same as this t star essentially. And as a result of that function call, we would have like the function of int pointer, and t would evaluate to int. And again, since we don't have infinite time here, for further reading, I recommend that you look at this CP reference page if you're interested in more detail of how partial specializations of templates are resolved. Okay, so at this point, we're done here. It took us about an hour, I think. And if you have any questions, please write them down in the chat, and I will answer.